Okay. We are very happy to have Vladimir today tell us about wave turbulence and loop diagram.
Okay, thank you. Very nice to be here. So the talk has 3 titles. The other one is renormalization and turbulence, or how storms develop as wind blows. This is work with Michael Smolkin. We had several papers, and more recently with Gregory Falkovich, who's here, and is the world expert on turbulence. So please direct all your questions to him. So the setup, it will soon become clear why this talk is being given to a high energy audience. So in short, it will be quantum field theory, but many things that we're used to will be very different and potentially more interesting. So the setup is one takes a calm ocean, then Atlantic or Pacific, then the wind blows. The wind excites some long wavelength waves. It's a nonlinear system. This generates, it interacts with other waves. You get shorter wavelength waves, and there's a cascade of energy from long wavelengths to shorter wavelengths. And what one gets is a statistically stationary state. The state is far from equilibrium. It's not the thermal state. It's statistically stationary. What came as a surprise to me is that this can be studied at weak coupling. And that's why we will be able to effectively use quantum field theory, because the problem is weakly coupled, and so things can be computed perturbatively. So it's weakly coupled if the waves are small. So this process I described goes into the name of wave turbulence. It's different from the turbulence that is more common in the popular imagination of hydrodynamics turbulence from Navier-Stokes, but this is also real. It occurs in many contexts. Of course, you can, if a storm develops, which is the second part of the talk, the waves can end up bigger, not small, have bigger angle, and then you get some white foam, which we know in the ocean. And this becomes harder, and of course, eventual goal would be to go from weak coupling to strong coupling.
What is H bar in this context?
There's no H bar.
You said it's quantum field theory.
The loop, I will illustrate how it's quantum field theory. So the fluctuations will be statistical. So so what I described, so is this blackboard visible?
Not yet.
It's a little in the shade, but we'll get used to it.
Just go out of the shade. And it's okay.
I forgot my sunscreen. So I should perhaps define what turbulence is. So turbulence, one definition is a state of a system with many degrees of freedom, which exhibits chaos in both space and time and deviates strongly from thermal equilibrium. Oh, hi, Dad. You have a haircut. It's like from 4 years ago. So that's turbulence. So the thing we'll be discussing in particular is weak wave turbulence. So there's some Hamiltonian describing the waves. So there's a Hamiltonian, which I'll soon write down. For right now, you can have like lambda phi to the 4th in your mind. And the nonlinear term, which will be quartic in our case, has small coupling. The coupling in front is small. So this is in distinction. So I want to make clear that this is in distinction from hydrodynamic turbulence. So hydrodynamic turbulence has Navier-Stokes equation. This is like cigarette smoke, because people don't smoke much anymore, or if you take fluid flow past an obstacle and then look here, then it becomes turbulent, then you need to put on your seatbelts and so on. So this is strongly coupled.
Well, actually, that happens in every airplane. Right? There's wave turbulence. But
That's right.
Behind.
All this one. So this is strongly coupled. So this is not what we are discussing. We will be discussing this, which will be weakly coupled.
You were talking about it as if you were thinking of surface waves.
Yes.
Seems like the dimensionality would matter too.
That's right.
I just want to be sure I was understanding
That's
properly.
right. So these waves that will be discussed, like the waves on the surface of the ocean, that is two spatial dimensions. That's correct.
But just to understand, so by taking that small coupling strong, we won't go from first regime to the second?
No, by taking from when this coupling, when the nonlinear term grows large, which it can because there's a coefficient in front, but there are momenta involved. This is like the waves on the surface of the ocean getting bigger and then breaking and then white foam forming. It's still describing wave turbulence on the surface of the ocean. The equations describing this are different.
What are the observables here?
Observables?
Yeah, what are you going to calculate?
The observable that's measured in the ocean is, which I'll discuss next, you measure the amount of energy in modes of different wavelength. So we can say the occupation number of mode K, and that's observed to be a power law over some range of scales.
But what do you even mean? It's not your quantum field theory. You observe what you observe, waves on the surface.
Read.
It exists.
So that's the quantity that's measured. The thing we want to know is what else can we calculate beyond that? So what are correlation functions? What are fluctuations around this turbulent state? Is this blackboard visible or it's the same shade?
Sorry, it's only the first few inches.
Okay. So I should have switched them, I guess.
Better.
So why am I giving the talk, and why is QFT necessary? QFT is not actually necessary for anything, but it's useful. In the same way that we're used to in statistical physics, equilibrium statistical physics, we use QFT even though it's not strictly necessary, because it becomes useful. The fluctuations here are statistical. And I think the progress that Misha and I were initially able to make was by using QFT methods, we can calculate things that without using QFT would have been much harder, even though you could do them.
Sorry, wasn't it done like long before you by some Zakharov or whatever? Wasn't it weak turbulence on the surface fully understood?
It was everything was fully understood at leading order, the nonlinearity, and it appears nothing was done beyond leading order. And the reason I think that was in people's mind, though I don't know, was the nonlinearity parameter is going to be taken small by definition. So you would assume that corrections to the leading order result would also be small.
But at any rate, you did go beyond the previous thing.
That's right. We're going to go beyond leading order. And the loop diagrams, which have more powers of the coupling, which you would think should be small because the coupling is small, they will have divergences. You have to sum a non-trivial class of diagrams. Things that from the point of view of QFT are natural to occur, that the actual expansion is not just the coupling, it's some other parameter. This occurs here as well. So the context.
That's a good one.
It works.
I don't think it's that great.
Sorry about that.
There's another one on the tray.
Actually, let me cross this off because we're not doing this. So the context is, let me write down the Hamiltonian. So as promised, there's a quartic interaction. So the variables A that I'm using, so roughly the field phi p is like AP plus AP dagger. So we switch from the real fields phi and pi. Pi is like phi dot to A and A dagger. A dagger is really A star, but this will help us all feel better if we write A dagger instead of A star. But these are real classical fields, and so it's more convenient to use the A variables like we do harmonic oscillator. So this is the Hamiltonian. There's a quadratic term and a quartic term.
And h is equal to 0 to answer the previous question. He considers huge occupation numbers.
So it's a classical field.
Yeah, everything's classical. The problem is classical. I will, part one of my talk after my intro, which will take half the talk, will be in 3 lines to show how one goes from stochastic classical field theory, which is what this is, to quantum field theory.
Okay. So until then, everything h bar is 0.
Yeah, the problem is completely classical.
And what is this field physically?
This field, the height of the ocean. The height of the
surface.
Yeah. Or other.
Is this something you can derive from fundamental principle, or you just
Yes.
postulate?
Yeah. In this paper by Zakharov and whoever, so wave turbulence occurs in many contexts. The surface gravity in the ocean is just one. You can take an elastic plate and hit it, and then you also generate waves. There are spin waves. So all of these situations have different lambdas, which are functions of the four momenta. So it's already immediately harder than QFT, where we take like lambda 5/4. Lambda is a constant. Light becomes simple. Here, this will be a function of these four momenta, and the only thing we will assume is that it has some definite scaling.
And K's and T's are both spatial momenta in 2 dimensions because we're on the surface.
The dimension is general so far, any spatial dimensions, but integer dimension.
So in terms that have like 3 creation, 1 destruction, you will have that.
You can do a canonical transformation to get rid of them.
Is this lambda completely generic?
Say again?
Is this lambda completely generic? Is the theory local? The coupling lambda. Is
Oh,
it completely generic? Is the theory local?
it's so omega k goes like k to the alpha. Alpha can be various powers. The coupling lambda p1 through p4, it has some definite scaling to the beta over 4, but then you can put any function here, which is a ratio of the momentum of the angles.
So the theory is not local.
It is not local. So for spin waves, this is just p1.p2 plus p3.p4. For gravity waves, it's a more complicated function, which has dot products p's to various non-integer powers and so on.
And there is no dissipation.
This is just the Hamiltonian, that's right. We will, in the actual ocean, there is wind. Yeah, we can say there's no dissipation. In physical problems, there may be forcing at long scales and dissipation at short scales. There will be some different forcing and dissipation, which we will add by hand and then remove, but you can say there's no dissipation. It's just a Hamiltonian system. So the basic question is, what is the occupation number AK dagger AK in a turbulent cascade? So the answer is no. The answer is nk goes like k to the minus gamma. Gamma is the spatial dimension plus 2/3 beta, where beta is the scaling of the coupling. So this is at leading order in the nonlinearity. So this was derived analytically by Zakharov in the 60s. It's called Kolmogorov-Zakharov cascade because Kolmogorov scaling for hydrodynamic turbulence, it's also nk goes to like k to some power, but that power Kolmogorov guessed on the basis of dimensional analysis. This power is derived at leading order in the coupling.
This is for large K or for
No.
any K?
This is k in the inertial range where this, this is derived at leading order in the nonlinearity, and then we have to ask ourselves what is the justified to just work in leading order in the nonlinearity, and the standard, I will give the standard answer and then
Tell us what is the cascade. That's why
Second,
Eliazar's question. You didn't tell us what is the cascade yet, and not everybody here knows.
there is energy distributed at various modes k, and the distribution of energy is not the thermal state. So it's a different distribution, which is n of k goes like k to the minus k. It's not the thermal state. So that's the cascade. There's energy cascading because it's not the thermal state, it's a far from equilibrium state.
Does this depend on how you're pumping energy into the system, or does that somehow not matter?
The standard law is it shouldn't. But we will see that maybe also needs to be refined because we may have IR divergence.
Somehow, the fact that we know physically that has to be going on isn't evident in what you wrote so far.
Oh, no, that's correct. That's not evident. But I will derive this or repeat. Yeah, we will derive this.
No, I meant to say, well, not just the answer, but somehow the answer implies this additional physical knowledge that something has to be sourcing the cascade.
She's
So-
absolutely right, Vladimir. May I interfere?
Yeah, please.
So wind excites waves of a certain scale. Those waves, however, by themselves will not be damped at all. They have to create smaller waves and smaller waves and smaller waves. And ultimately, if you get to small enough scales, perhaps you can kill it just like Kolmogorov. Only here, Zakharov did it analytically. Kolmogorov as Vladimir, you are right?
Yes.
As Vladimir said, Kolmogorov just postulated. Am I being fair?
Yeah.
I guess what I was just commenting on is that in that Lagrangian or Hamiltonian formulation, you don't seem to see that at all.
That's right. That's right.
You'll come
It's
back
not
and
obvious.
explain
Yeah, it's
that.
not at all is. And again, this is only at leading order of the nonlinearity, so we will have to derive equations for how the occupation number changes with time, and then look for stationary solutions, and it will come as a surprise, at least to me, many people, that there, in addition to the thermal state, which is what we normally think of as the only stationary solution, there's a second one, which is this one. So our goal,
Is this different distribution of turbulence related to some existence of some other conserved quantity, like when you have a chemical potential? So you have a raw density that is.
Yes, it's a second cascade, it's an inverse cascade.
so total energy, I mean,
I'm just saying that you can have
Yes.
the minus beta H,
Yeah.
you could have.
I see what you mean.
but
Yes,
you-
so you're correct. So energy is conserved and total occupation number is conserved, but the solution, the reason you actually managed to get a second solution is, I'll describe later, a second stationary solution, is this isn't valid at k equals 0. So that acts as the sink, which makes it okay. So our goal was initially quite modest. We just wanted to know what are the leading order corrections to this. What are the higher order corrections?
But sorry, then I was wrong. So energy does not go to small scales. So Grisha said something about number of quanta. So there are two conserved quantities, or what?
We don't consider the second one, only direct cascade
Of energy.
of energy.
Okay.
So the initial goal was just to ask what are the higher order corrections. So people spent 50 years doing tree level, which in Feynman diagrams we would draw as this interaction, just the tree level interaction, leading order lambda, and we just wanted the higher order. Like this. The higher order corrections, which will involve loops So this is what we wanted. We wanted to compute the loop diagrams and see how this changes the Zakharov solution. And we also wanted to compute higher point correlation functions. So all the focus has just been on the occupation number, which is the 2-point function. So we just wanted higher point correlation functions. So that was the initial goal.
So you said this is a classical field theory, but there is a loop. There are loops.
But there are
loops.
That's correct. Yeah, I'll explain that. There are fluctuations. So the point is, it's a chaotic system. You have to average over something. So you either average over space or time, or you add some, or phase space, or you add some, which is what we'll do, some random forcing and dissipation, and then take those to zero at the end.
Do you have parameter to count loops?
Well, it has the lambda.
The number of lambdas. Lambda is not precisely the number. It's like the usual. Right?
So each bar counts loops. That's the point.
Let's come back to this when I write down the
Thank you.
And again, this was never computed because the assumption was always that the corrections to this would be very small because we're assuming lambda is small. And so in the process, we discovered that there are divergences to the loop diagrams. There are UV divergences of various kinds. There are infrared divergences. And so one has to resum some class of diagrams. And so the standard lore becomes false, which isn't surprising because I'll show that this is directly analogous to what happens in quantum field theory. And so we discovered that we need the machinery of renormalization.
What are the units of lambda? Is it on the dimension?
Yeah, lambda has units of lambda has units. I have to count. It has
units in general. So when you say it's small, what do you mean?
Good. So lambda has a prefactor. So we set the prefactor to be small. But then since this depends on momentum, the nonlinearity will be large either in the UV or in the IR. And so generally, it's general choices of parameters. It becomes the nonlinearity becomes so the general lore was that the solution will be valid in the region where this remains small. So the assumption is that there's locality in K space. So if you don't know about loops, then you have some assumption about locality in K space. You say in this region of K, the lambda is small because you have to say for which momenta you're talking about, and then you say it's okay. But so you would pick all these 4 momenta to be such that about the same order, such that lambda is numerically small. But then we know that if you compute loops, then the momenta that run in the loops can be arbitrarily large or small, and so you will have exited this regime that you thought you were in. So this was our initial goal, so we discovered new turbulence, and now our goal is more ambitious. We effectively want the beta function So in this context, what that means is we want to know what happens deeper along the cascade. So let me be more explicit. So there's the parameters here that enter omega k and lambda p1, p2, p3, p4. So these are known. So these are the bare values. They're known theoretically because one can derive them, and they're known experimentally. And the way you would experimentally measure them is you would take a tank of water or something then set up two waves of momentum P1 and P2, have them scatter into waves of momentum P3 and P4. The state is not turbulent, it's just there's nothing else except the waves you made. So those are, that's what lambda is.
So, because in principle there are also sextic couplings, etc. And when one sort of trying,
so there are two. So for some systems there's no sextic coupling. Like if you take the nonlinear Schrodinger equation, that's a case that has turbulent cascades. It's just quartic stops. You're right for the surface gravity waves. There are higher order terms, which I'm not writing because they are supposed to be even more suppressed. But you're correct. If we're going to higher order the nonlinearity, we should at some point start including those as well.
Suppressed by what? Like physically suppressed by what?
The waves. So we're assuming the waves are small. So they're not very large waves. And if the waves are small, these higher order terms will have more powers of, they'll come with more powers of A. It's just like irrelevant operators. So, so this uses scattered two waves in a non-turbulent state. So now we turn on turbulence, so we take the ocean, we turn on wind, we get the turbulent state, and now we again want to measure the scattering of two waves, but the 4-point function we're going to get is going to differ from lambda, and we want to know by how much it differs. And the difference will grow as the momenta increase. So we want to know, is the interaction weaker or stronger than it was without turbulence?
Just to make sure I understand, this is idealized, right? Because you're scattering two waves with a given frequency, right? And any real wave will contain multiple frequencies in it.
Yeah.
Yes. Yeah. Okay.
Yeah. What I wanted to emphasize. The reason I wanted to emphasize this is that in QFT, nobody ever measures the bare coupling constants. We are free to add counter terms to them. What we measure is a renormalized coupling constant at some energy, and we couldn't care less what happens to the bare one. Whereas here, we actually know the bare coupling constants. And so here, the distinction will be that, like in, well, I'll get to it later, but roughly like in lambda phi to the fourth theory, the beta function is positive. You get that the coupling grows with energy. And if you were to fix the bare coupling, you would conclude the coupling at some finite energy is just going to zero, which would be nonsensical, but you don't do that. You fix it at some finite energy at which you do the experiment, and then you have a finite coupling, and you don't care that the bare coupling is going to infinity. Here, the bare coupling is fixed. So an analogous thing will happen, and then it will truly be the case that the renormalized coupling is in fact going to zero as you're removing the cutoffs. Okay, so I was correct with the intro took half the talk, so let me give the outline. So part one, I'll show that stochastic classical field theory is equivalent to quantum field theory. This has been known to many people for a long time, but it's never been applied to wave turbulence, as far as I can tell, this knowledge. Many attempts have been made to apply it to Navier-Stokes turbulence, but at first approximation, none of those really got anywhere because Navier-Stokes turbulence is strongly coupled, so we can't really solve strongly coupled field theories in general, so that won't help much. In part two, I'll discuss the kinetic equation of wave turbulence. So this is looking at how the occupation number changes with time, or at leading order in lambda, the thing that has been known for a long time, and part three will be loops. And as I said, we will, when discussing loops, we will find divergences, and then we will sum the most divergent diagrams.
Vladimir? What do you mean by stochastic classical field theory is equal to QFT? Can you compute things like probability amplitudes in stochastic classical field theory?
Can you compute?
Probability amplitudes, not probabilities. Can you define those in stochastic classical field theory?
We'll be discussing correlation functions.
Okay. I just don't like that equal sign.
I think you mean in Euclidean.
Well, let me do the derivation. It will be 3 lines, and then no, it won't even be Euclid. It won't be. Let me do the derivation. It's 3 lines.
Sorry, just to check my memory, I remember the Langevin formulation goes, there's a difference in dimension. And
You don't need to worry. I'll do the derivation. It'll be 3 lines. For this part, it's actually harmful to use previous knowledge because the derivation is trivial. So part 1. So if we take, we have some equations of motion, ak dot minus I dh ak star, or ak dagger. And then what we're going to do is, so as I said, we have to average over something because the system is chaotic. In the actual real world, when you do the measurement, the averaging is mostly over time. We instead, the averaging that we do, because that's what many people do, is one adds a stochastic forcing, white noise. So this is drawn from a probability distribution. K of t squared over f of k. So one adds some stochastic forcing and some dissipation, and then we will, in the end, take the variance of the forcing and the dissipation both to 0 while keeping the ratio fixed. Good. So that's the setup of the problem.
You called NK the occupation number, so is it just using 2 different lines?
Yeah, so technically this is, right now I'm using notation that fk over 2 gamma k. I'm just going to call that nk. The reason I call that nk is because at leading order in lambda, we will find that this will be the occupation number. So that's how you control occupation number, by controlling the ratio of forcing to dissipation for mode k. So this introduction of forcing and dissipation is a trick because this is an easier averaging to do than an averaging over time. And it's assumed that this trick is equivalent over different averagings, but it's not obvious if that is or isn't true.
So these forcing and dissipations are not related to wind?
No, these are fake forcing and dissipations, which we will remove. In fact, we can do the calculation without doing forcing and dissipation by perturbatively solving the Liouville equation and doing a phase space average without ever introducing forcing and dissipation, but this is slightly easier, so that's why I'm doing this. So if we compute an expectation value of some combination of A's, so this is the part where I'll show this as a Q of T. So we average over the forcing of A. But really what this means is for each forcing, we need to impose the equations of motion for A. So delta function for equations of motion for that forcing. Good. So that's what we mean when if we were to want to compute the expectation value of, say, the number operator AK dagger AK or something else, we would first solve the equation. We would pick a forcing from this Gaussian distribution. We would solve the equations of motion for A. We would compute AK dagger AK, and then we would repeat for different forcings and do this integral. That's how we would actually do this.
This is at fixed time?
The A's can be at different times. It doesn't matter. This is the argument is general. So the thing what we're going to do is this delta function of the equations of motion with fixed f. We're going to write this as d eta, e to the eta equations of motion. So just integral. And after writing this as an integral, we then integrate out the forcing, because it's a Gaussian integral, because it appears linearly in the equations of motion, it appears quadratically here. We integrate out the forcing, and then we integrate out this field, this Lagrange multiplier field eta that we introduced, and we end up with a path integral dA, e to the minus integral dt, equations of motion with no forcing, squared divided by f of k.
Come back to those things, there is no I. It's like Brownian motion.
There's no I. Say again?
It's like Brownian motion.
It's like?
Like the three-particle path integral, when you rotate, it becomes Brownian motion in quantum mechanics.
Yeah, so this goes under the name of Martin-Singer-Rose. If you're in condensed matter, then that means something to you. But anyway, it's just 3 lines. So this is how we went from a stochastic classical field theory to a quantum field theory. We're now integrating over the field A, so A has become a quantum field. And our Lagrangian is just the equations of motion squared. So it has a quadratic term, a quartic term, and so on.
And when you say equations of motion, you mean the one without forcing?
That's right, with F equals 0.
Dissipation.
That's right, the one with F equals 0. With this, keep the dissipation, but no Fk. But then at the end, we will need to set Fk and gamma k. After we've done the calculation, we will then set Fk to gamma k both to 0 while keeping this ratio fixed.
And this functional integral is on A of t, I imagine, or some.
Yeah, it's an integral over A of t. That's right. It's
now with some initial conditions.
Very good. So this is a point I glossed over. Indeed, there should be initial conditions. The point is because of our dissipation. So if I were doing these integrals, so if I now compute the Green's function for the field, I should technically account for the initial conditions, and then it may be a complicated Green's function. The point is because of the dissipation, the initial conditions drop out and they don't matter. So it's like if you take a harmonic oscillator with forcing and damping, it doesn't matter what initial conditions you pick. At late times, the motion only depends on f of k and gamma of k. Everything else drops out. So the same happens here. So that's what we get here. All of this is predicated on having a stationary state. So we assume we have a stationary state, then we assume time independence, then we do this, and then we will get equations which we will need to solve to ensure that we have a stationary state. And that will be either the thermal state or the turbulent state. Good. Okay, is everyone satisfied that we have?
So far it's ancient history. We want new results.
I may only get to those after the talk ends.
That would be cheating.
Okay, I have 3 more minutes of ancient history, then we'll have new results. So part 2. So using the equations of motion, we can write down dak, value of dak. This is the imaginary part. So using the equations of motion for the Hamiltonian I wrote down, one can trivially derive this relation between the time dependence of the 2-point function and the 4-point function. If you now take for the 4-point function and use the Feynman rules you get here and compute the tree level 4-point function, it goes like lambda. The Feynman diagram is the one I drew, just a tree. This thing, you get the leading order kinetic equation, so at tree level. So you get P1, P4, delta K, P1, M1, 2, 3, 4 squared, delta function omega P1, So this is the tree-level kinetic equation. It expresses the n dt in terms of some other n's. This is the wave analog of the Boltzmann equation. So you, as this picture illustrates, if you're interested in the occupation number of mode k, you can either gain something or lose something. You gain if some other modes 3 and 4 scatter into mode k and some other mode, or the reverse process, and then you lose probability in mode k. So this is like the Boltzmann equation, but for waves instead of particles. So so we're interested in stationary solutions of this. And the obvious stationary solution is the thermal one. K is some constant divided by omega k. This is the Rayleigh-Jeans solution. It's just the high temperature expansion of the Bose-Einstein distribution. If you plug this into here, it's obviously a solution because here you get omega p1 plus omega p2 minus omega p3 minus omega p4, which is precisely vanishes by the delta function.
What is T? What is T?
P?
T. Temperature.
Temperature. This is temperature. Just take, it doesn't matter. Take 1. So this is one stationary solution. And this is a thermal one. The thing that Zakharov discovered in the 60s is that there's a second stationary solution, which is nk plus k to the minus gamma, where gamma is d plus 2/3 beta. So if you plug this into here and do an interesting change of variables, you will see that the right-hand side vanishes. And again, we found a stationary solution that's far from equilibrium at weak coupling. So the coupling is still weak. This is just at leading order in lambda. Good. Okay, that's the end of review. So then we start computing loop corrections. So again, the procedure is straightforward. We want to compute a 4-point function. It's actually equal time 4-point function, which appears there. It's straightforward to compute because we have a Lagrangian. It's the equations of motion squared. We have Feynman rules, so we can it's straightforward to do the calculation. So we start computing loop corrections to this tree-level 4-point function, which just had this diagram. So this loop integral, it has the coupling lambda 1, 2, 5, 6, 5, 6, 4.
So loops like self-energy correction, they vanish?
No, they're self-energy corrections. The one at order, this one is trivial, it just renormalizes the frequency, and the next one, the Mellon diagram, is higher order in lambda, which is why I'm not discussing it.
I was asking about this one. So this one is like a kind of trivial.
This one is trivial, it just renormalizes the frequency. And the Mellon diagram one is higher order in lambda, so. But we will need to compute those two.
Mahesh,
Yes?
if I choose to work with the previous description before integrating out F,
Yes?
I can think of these loop diagrams as tree diagrams, but connected by lines of F.
Correct.
So, but F doesn't carry any momentum. So, do you really sum over all momenta in 5, 6, or do you?
Yeah, you sum over all momentum. Yeah.
But how do you see that from the description using Fs? The F don't carry any momentum.
No, F is momentum.
Yeah, F has momentum. It has a subscript K.
Oh, okay.
It was just white noise, so its 2-point function was just F of K. No, F has momentum, and its variance, and yeah.
Thank you.
So this loop diagram is a correction to the 4-point function. If you, so this can have multiple divergences. So it could have UV. So could have. So analyzing this is not trivial because the lambdas are functions, which are non-trivial functions. It's not like lambda divided by the fourth, where lambda is a constant. So there are different kinds of UV divergences. So there could be a UV divergence when P5 goes to infinity. This is usually doesn't happen. There could be a divergence, IR divergence, when P5 goes to 0. The answer here is usually yes. And the divergence that we're actually most interested in is when P2 goes to infinity. So this is not something we normally do. You take a 4-point function, but then ask how it behaves when one of the external momenta goes to infinity. The reason we do that is for the kinetic equation for computing, right, you could say this composite operator, you have to sum over the momenta. So this would be a UV divergence of a composite operator. And this is the divergence we're interested in. So as you take P2 to infinity, this will diverge. Good. So the initial logic was there's no need to compute corrections to the tree level result because they will be small, because lambda is small, but that argument becomes false if one has other scales around and one has other scales, the UV cutoff, the IR cutoff, which one gets from divergences on those. So the question is, what are we supposed to do with the divergences? So the divergences aren't a problem at all. It just means the perturbative parameter was not lambda like we thought, but it's something else. It's the loop integral. So what we do is what we do in QFT, we sum diagrams. So we just add more bubbles. So we sum all these diagrams. It's exactly the same as summing the leading log divergences in lambda 5 to the fourth.
So
yes.
Is it exactly the same? Do you have a margin of deformation?
No, okay, it's not. Sorry, I take it back.
You have a power correction here.
Yeah, it's not
more
exactly
like
the
a
same.
non-relativistic scattering
Yeah.
into theory. Like,
Yeah.
like
It's not exactly the same. The diagrams are the same. Many other things are different. Indeed, it's not a log divergence, it's a power law divergence. The divergence is of a different type. It's not because the loop diverges, it's because the external.
Because in 5 to the fourth, you don't have just the sausage, you also have other, you have the cross diagram. Here you have just the sausage diagrams, right?
What's the cross diagram?
The one where you have, I mean,
different channels? Or?
Yeah, different channels.
Yeah, that's right. Okay.
That's like the scattering of non-relativistic particle.
Yeah, okay. Exactly. It was too strong of a word. You sum some. So if we do this, for our case, and so doing this for general lambda is hard because the different internal momentum integrals won't decouple. So we assume we're going to do it for a special kind of lambda, one which has a product factorized form. So we assume, so for lambda 1, 2, 3, 4, that's of this form, lambda 1, 2, lambda 3, 4. Then these integrals factorize, and we can do the sum, and we find that the kinetic equation, or the tree level, the 4-point function is like the tree level answer with an effective coupling, which is lambda 1 minus L. So it's just a geometric sum. And this is again analogous to summing the leading log diagrams, and this looks like the effective coupling that you write down for QED or lambda 5 or 4. Usually you write down a beta function, then you integrate the beta function, but that's equivalent to summing these diagrams.
So this lambda effect is not that form anymore, right?
That's right. This is the.
So isn't that the problem? The ansatz is not stable under G in other words, right? So this factorized form.
That's right. So I just take I take a system in which the bare coupling is of this form, like lambda could be P1, P2, P3, P4 to the beta over 4, and then I do this sum.
And in the loop, you have a power divergence.
In the
you have power divergence.
So the point of doing this was to cure the divergence that happens here when P2 goes to infinity, and we need to integrate the 4-point function over P2 in the kinetic equation. This cures this
So right now, the diagram P2 is fixed, right?
That's right. Now, if you insert this 4-point function into the kinetic equation and integrate over P2, it's now UV finite because this, as you were taking P2 to infinity, L was going to infinity, but now it's in the denominator, so now it's finite. We discovered along the way.
The denominator, that L grows with P2.
Correct, correct. We also discovered that L can often have an infrared divergence, but that's a different issue.
But lambda 1, 2, 3, 4 also diverges as P2 goes to infinity, right?
That is true, but it didn't diverge in a way which was a problem for the kinetic equation. So even the tree-level kinetic equation had a window, a non-trivial window of convergence, and the Zakharov solution fell in that window. By power law counting, you wouldn't have seen this. It was important in the tree-level kinetic equation that there was a difference of terms. Because by power law counting, you would conclude the tree-level kinetic equation is either divergent in the UV or the IR because it's just powers. So that's why it's actually difficult to assess the divergence of diagrams because you can't just use power law counting. The cancellations are important. You just use power law counting, there's no turbulence. You miss the turbulence state.
But why that ansatz on lambda just because then you can...
Say again?
Why that ansatz on the lambda equals square root of...
Oh, no reason. It's because we need to do this sum, we need the integrals over this momentum and so on to factorize. If they don't factorize, we can't do the sum. We can just write an integral equation for the effect of 4-point for the 4-point function.
But I mean, it's a bit strange, right? Because it's factorizing momenta 1, 2, 3, 4. So
yeah. So here, this is 1, 2, 5, 6, 7, 8. So here there's a lambda 5, 6, 7, 8. I need to split the integral over P5 and P6 from P7 and P8.
Yeah, but say the C, the real C, would oblige with that.
No, the real C does not have this form. So for the general case, one has to solve an integral equation to sum these diagrams. I won't bother writing down the integral equation. Running low on time. So the general case to solve this, to sum these diagrams, you have to write down an integral equation and solve that. So that's what we'll need to do for the real C.
That was done.
Huh?
That was done.
What was done?
Doing that in the real case.
Solving the integral equation of some of these
you haven't done it. Yeah.
Oh no, we have not done that. No, that's hard.
So you will not tell us about the ocean. You promised the ocean.
No. I'm much closer to the ocean than probably many other talks you've heard in this room. So.
That's a low bar. Is there some physical system that does factorize?
So we can also do it for if you do some factorization. And this occurs for, so then the answer is different when we computed that too, and this occurs for spin waves. For spin waves, lambda 1, 2, 3, 4 is P1.P2 plus P3.P4, and then we can write down the answer. It's slightly different from this, it's several geometric sums. So that's a physical case where we can write down the answer. But again, in this physical case, we wrote down the answer is just an integral equation which you have to solve numerically. So we just haven't solved it yet. It's not done.
Last year we had to talk how to sail a boat. Last year we had to talk how to sail a boat in this room.
So I'm almost done. So one thing I said before, but let me say again, in QFT, no one measures the bare coupling constants, and we by experiment demand that lambda be something that we measure at some finite energy, and then if it goes to infinity, as the energy goes to infinity, then so be it, we don't care. Here the situation is different because the bare lambda, this one here, is the one that's actually measured. And so what this form seems to indicate is that if you are far from the cutoffs, far from the cutoff where you're measuring this, the effective coupling is in fact going to 0, and that's just what's happening. This equation doesn't look surprising from a QFT perspective, but this result when applied to waves is surprising. That since L is infrared divergence that as you take the box larger and larger, the 4-point function that you measure changes for momenta that are very small.
So again, what is the propagator here?
I never wrote it down. I can write down the propagator. In position space, dk of t is nk e to the I omega k times t minus gamma k absolute value t. That's the propagator.
That depends on the choice of the f, right?
Correct.
And
Nk is fk over 2 gamma k. That's right.
Okay.
That's why it's important to keep f and gamma finite until the very end.
But how does it go with k? Because that would cut off whatever you want, right? I mean, the ratio f over gamma is completely up to you, right? So you could have chosen an n of k that's 0 above some frequency.
So n of k needs to be k to the minus gamma, where gamma is that scaling, otherwise we don't have a stationary state. So it's not up to me. So it was not up to me initially, but then to get a stationary state, it's no longer up to me. It has to be either the thermal state or this kz state, or otherwise we don't have a stationary state. It's nothing to discuss.
Or what is the inverse cascade?
So the inverse cascade is something different. So nk, this goes like k to the minus gamma, where gamma is d plus 2/3 beta. So when we make statements about divergence, what we do for this lambda, we plug in its various scalings under different momenta. For n, we plug in p5 to the minus gamma, and for omega, that's p to the alpha, and so that's what we do. Okay, so let me conclude. So one thing to say is that in QFT, when we're doing RG, we flow from the UV to the IR in the sense that the theory is specified in the UV, the quantity is reinforced in the infrared, and so that's what we'd like to compute. In turbulence, the situation is the opposite because the cascade is going from the infrared to the UV. So wind is forcing in the infrared, and we don't really care what happens very deep in the UV. That's where dissipation is. So we're going in the opposite direction. So let me list the things that we still need to do. So we had some infrared divergences. It's unclear if those go away or not if we sum more diagrams. Unlike in QFT, they don't have to go away. This has occurred in turbulence context before, where the correlation functions one get do explicitly depend on the infrared cutoff. It would be nice, the way we did RG is somewhat non-standard. It's like RG in the 60s, which is like discussed in Feynman's book on computing the energy of an electron gas. You just find the most divergent Feynman diagrams and then sum them. So that's sort of the stage we're at. It'd be nicer if we did more systematic RG, but that's slightly confusing. Slightly confusing at this time.
But the RG, you do it in this case when you have marginal deformation. You don't have marginal.
No, you can do RG with relevant or irrelevant.
Well, I mean, yeah, it's all dominated in the end.
Good. So
right?
indeed, that's
not
why.
Really an RG.
Good. So here we're not. So we weren't trying to do RG. We were just trying to say we want the corrections to the tree-level kinetic equation. We draw a Feynman diagram. This is the correction. We find that it's infinite, and then we say, okay, we need to resum some class of diagrams. It took like a year to realize that what we're doing is basically RG. It's the same diagrams with someone computing the beta function. So we can call it something else, but that's effectively what we're doing. The lesson is the same, that the expansion parameter is not lambda, it's this loop integral. Because there's additional scales, the UV and I are cut off.
You want to address the sign of the...
Yes, so like in QFT, there will be qualitatively different behavior depending on if L is positive or negative, just like there's qualitatively different behavior if the beta function is positive or negative. But here it's more elaborate because L is not clearly of a definite sign. So that still needs to be understood. Yes?
If you go to higher loop,
yes.
Is your statement that you have identified the correct expansion parameter born? Does it work? You can see indications in two loops that you have found the correct expansion parameter?
So the most modest statement is that this diagram diverged. And if you sum those diagrams, then that gets rid of that divergence. A stronger statement is that that these are the most divergent diagrams at any order in lambda. Grisha, you wanted to make, how about you make the comment you wanted to make?
About what?
The sign of L.
Yeah, that's your talk, but well, I can make a short comment. What I find the most important result of it is not probably what Vladimir finds the most important result. So we actually can consider in one particular class of things when the infrared divergence dominate, then we can say what is the sign of L of this loop integral, and I find it beautiful. I think this is the most important result. And it is in such form. So if my omega k is k to the power alpha, and then my lambda has some definite sign in the infrared, namely when there is k1, k2, k3, k4, and k1 is much less than k2. So in this limit, I assume that it has a definite sign. Then the criterion that the sign of L, the slope integral, is minus lambda 1 minus alpha. Or I can write it differently if somebody knows what is modulation and stability, or what is Bogoliubov spectrum of fluctuation of condensate. So it's actually, let me write in the following form. The second derivative of omega k with respect to k, which is the sign of this, right? This is just a second derivative times the second derivative of omega k with respect to the amplitude. So essentially, this is for a single wave, it's a criterion of modulation and stability. So if you have a wave with a given wave number, and or if you write a spectrum of Bogoliubov fluctuation of condensate, what you find out that your omega as a function of q is something which is the square root of omega 2 prime lambda q squared. So if this product is plus q to the 4, so if product is negative, your fluctuation, your condensate is unstable, right? So in a sense, what I find unbelievably beautiful is that in this turbulent situation, at least there is a class of models where we can say where it will be confinement type situation. Positive L, it's, this 1 minus L, that means that you have a pole, which means that as you go along the cascade, you pass from wave big turbulence into something which will be dominated by bound states. And I believe that this bound states is exactly form, and this breaking wave, some of them Stoch waves, is 120 degrees. So what I think is our new renormalized kinetic equation ideally would have two solutions. One at the low limit of k would be big turbulent Zakharov solution, and another in the limit of large k would have strong turbulent solution, confinement type, namely dominated by bound state of plane wave. Plane waves aren't really right objects, so in this sense, shocks, solitons, or these cusps are our hadrons. That's what I find. But this is something which is done for a very simple model, not for true lambda, for gravity waves, for surface waves, where we need to solve complicated equation. But at least in one class, I find this our most important result. But then again, it's my perspective on because what you see as the wind blows stronger and stronger, you see more and more form, which means that you pass from this type of a C to that type of a C. Right? And this will be something, a solution which would be determined by this denominator and not by whatever stands here. That would be irrelevant.
But didn't you say that you always become more and more nonlinear as you go to smaller and smaller scales, even if the wind is weak?
Because when your L is negative, you are in
No, I'm not talking about L. There is no L. There is waves on the surface of the ocean and there is wind. Suppose wind is not very strong. Don't you still get cuspy things on small enough scales?
Yes.
You do, right? So basically you are saying
it's about the length of your cascade.
Right, so basically the result is that you do go beyond Zakharov always at small enough scales, and you claim...
We did not prove it for C waves, we prove it for much simpler
Right, I
model.
understand.
But essentially, on a slogan type level, I would say this is how non-locality enhances non-linearity in non-equilibrium. There are three known here, and they all enhance each other.
So Zakharov only works for a certain extent. Beyond that, you guys come into the game.
Not in all cases. For C waves, we believe that L is positive. But for example, in other situations, for example, for Gross-Pitaevsky or other cases, this could be negative.
And that Zakharov is always right.
Even better and better. So as you go to larger, it's like quantum electrodynamics, right? So you go forward and you actually decrease your effective interaction, which is essentially says that I have forward scattering and my multi-wave correlation decreases. If it increases, you are in confinement. If it increases, then you are in a Moscow zero and you just live happily.
Why did it take you 60 years to do this?
I don't know. I don't know why Polyakov and Zakharov did not do it 40 years ago. Because we were discussing this with Polyakov 30 years ago. Polyakov started to do it.
Okay.
And then was distracted, gave it to a student, the student didn't.
But you agree, it's pretty natural.
This was a scary one in the course for 10 years. I was doing my PhD when I first see this divergence, and I've shown it to people. Say, well, divergence, forget about it. It's something nasty. You people know that divergence is a tool, and in my community, divergence is supposed to be a nuisance. You kind of try to forget it. So it took me 40 years, to meet Vladimir and then to do all this.
But also, sorry, since these waves are simple enough, cannot you numerically prove that indeed this is what happens in form coherence?
Lambda for surface waves are unbelievably complicated. It changes sign on a very complicated surface.
You are saying you cannot do it numerically?
Well, we're doing it numerically, but numerically it's a very non-trivial task. Oh. Even numerically it's very non-trivial task. But spin waves, for example, we do analytically all the way. There are many others, and plasma, in a sense, is. You can prove, for example, for non-isothermal plasma that it's getting better and better. That as you go along the cascade, it's getting more and more big.
But do you not have a direct?
So what about if we stop and thank the speaker and then we continue?
Sure. I'm not going to speak.
Any more questions?
I have, but I don't.
Now you are allowed.
No, seriously. This is very simple. This is classical physics. Do you have a definitive numerical proof that you do become nonlinear and that your theory roughly works?
For surface gravity waves?
For surface gravity wave or for some artificial system?
For artificial system, we do it analytically. Absolutely.
Even analytically?
Yeah. We just compute analytically for these two cases. But for surface